Once again, you are welcome to my channel. And for those of us that have followed meticulously throughout this series of electricity and electrical components, you'll quite agree with me that in our last class, we dealt extensively with electric fields, its application, and its effects. Then in our last class, we looked at series and parallel circuits 1. That equally gave us the opportunity to carefully dive into Ohm's law, Ohm's rule, how potential difference is related to current, and how the constant of proportionality was established. And we call K R, and R represented the resistance of the resistor. We say that R is key to the efficiency of every electrical component or electrical wire or metallic conductor, because a large R shows a smaller I. We established that in our last class. Please, for the purpose of understanding, you can check that out in my last video for clarity. And a smaller R, of course, begets a bigger I. Now, for the purpose of today's class, we have some prototype questions that are carefully tailored for the purpose of solving problems with respect to V, I, and R. And our Ohm's law, which is V equals to IR, it's a very handy formula here that we shall be using throughout the purpose of this particular teaching. So I indulge you to stay calm, listen carefully, make sure you are with your writing materials, for it's going to be an interesting class. So let's quickly dive into the question. With me here is our first question. And our first question here states that in the figure below, calculate the total resistance. So we're looking at the total resistance figure A and B. In the figures below, calculate the total resistance. Remember, we established earlier that the total resistance R in a series connection is given by R1 plus R2 plus R3 plus Rn plus Rn. So all we need to do is the summation of all the resistance to arrive at the equivalent resistance of the sum. And here we have R1 as our 5 ohms, R2 as our 10 ohms, and R3 as our 6 ohms. So that can be represented by slotting it into this particular formula. And you have your equivalent R to be 5 plus 10 plus 6. And by the time you sum this up together, you have 5 plus 10 is 15. And 15 plus 6 is 21. So the equivalent resistance of these resistors is 21 ohms. Is that okay? 21 ohms. That means you must always remember this formula in order for you to solve problems with respect to resistors that are connected in series. Okay? Then we move on to the next question. The next question states that we should equally find the equivalent resistance of these resistors that are equally connected in series. We have another series problem here, and similarly we just slot in our equivalent resistance, becomes R1 plus R2 plus R3, because we have three resistors all connected in series. We have our first resistor, which is R1 to be 4 ohms, our second resistor, R2 to be 1 ohms, and our third, the last but not the least, is R3, the last but not the least, which is our 7 ohms resistor. So we just carefully slot it into this our formula. R1 is 4 plus R2 is 1 plus R3 is 7. And by the time you sum it up all together, you have 4 plus 1, 5. And 5 plus 7 is 12. So you have 12 ohms as your equivalent resistance for the 3 ohms resistors, 4, 1, and 7 ohms respectively, all connected in series. Is that okay? So let's quickly move on to the next question and see what it entails. Hope you're understanding what is happening here. Peradventure, there are areas of discrepancies or areas you did not quite understand. All you need to do is to write me in the comment section, and I will attend to your needs. Thank you very much for being part of this teaching. Please try and subscribe to my channel. Give me a like, and as you do that, I know you are moving forward. Thank you very much. Now, let's move on to our third question. In our third question, we have a network of connection that is made up of set of resistors all connected in parallel, and that is being powered by a cell here. We have our battery B, and we have a network of 5 ohms, 6 ohms, and 3 ohms resistors all connected in parallel. So this is an example of a parallel connection. Remember, we do establish that in our last class. So now, and we reminded ourselves that in a parallel connection, you have this particular rule that guides its establishment. We have this particular rule. That guides it. 1 all over R is 1 all over R1 plus 1 all over R2 plus 1 all over R3. Right. So we can slot in our values, and at the end of it all, we have 1 all over 5 plus 1 all over 6 plus 1 all over 2. And we can find our LCM from here. So finding our LCM, Let me write this R well. It's looking more like a Greek alphabet. R, yes. The LCM was 5, 6, and 2 can be 30. Yes, it can be 30. It can be 30. 30. So we have 30 here. 5 into 30 is 6. 6 times 1 is 6. Plus 6 into 30 is 5. 5 times 1 is 5. Plus 2 into 30 is 15. 15 times 1 is 15. So we have this 5, 6, 6, 5, and 2, 15. So let's sum up our numerator. Let's sum it up. 6 plus 5 is 11. 11 plus 15 is 6. 26. We have 26. We have 26. So we have 1 all over R equal to 26 over 30. So we have 2 here is 15. 2 here is 13. So we have our, I can delete this so that we have more space for our problem. So we have 1 all over R is equal to 13 all over 15. When you cross multiply, you now have 13R equal to 15. And you have your R equal to 15 by 13. That's your equivalent resistance of these resistors that are connected in parallel. We can equally solve this particular problem by using a standard formula for a set of resistors that are connected in parallel. And that, of course, will arrive at the same answer. So we're doing that in a jiffy. But remember what I did here is at this point, I divided both sides by 13, divide right-hand side, and left-hand side by 13. That's what I did here, and I arrived at our R equal to 13, because of course 13 by R, 13 over 13R equal to 15 over 13. 13 takes away 13 and you have R equal to 15 over what? 13. Is that correct now? Ohms. Remember your answer is in ohms. R is in ohms. Yes. Which is represented as omega. Are we all together? And that is how I arrive at the effective resistance of the 3 resistors that are connected in parallel, the 5 ohms, the 6 ohms, and the 2 ohms. The effective resistance of these 3 resistors is 15 over 13 ohms. Is that clear? So we're moving on to the next question. Moving on to the next question. Please, if there are areas you did not get, you can still put down your question in the comment section. I will attend to them as quick as possible, as fast as possible. Thank you. So now we move on to the next question, the 4th question in the series. And here we have a connection here, a 2 ohm and a 4 ohm resistor that is connected in parallel alongside a 15 ohm resistor in series. So what we do here now is we first simplify the parallel connection, and thereafter we sum up the resistors in series. So let's start right away. Now we have from our formula. Remember in our last problem, that keep my mind, if you have a set of resistor 1 over R equals to 1 over R1 plus 1 over R2. Let's establish this before we solve this particular problem. This can equally be represented as R1 plus R2 all over R1 R2. Is that correct? Plus 1 all over R3. Is that correct? The LCM of R1 R2 is R1 R2. Thus the LCM of R1 and R2 is R1 R2. R1 into R1 R2 is R2. Is R2. Is R2. Is R2. While R2 times R1 is R2. Then R2 into R1 R2 is R1. Is R1. Is R1. Yes. Are we correct? The LCM of R1 R2 is R1 R2. Is R1 R2. Sorry? Is R1 R2. Then R1 into R1 R2 is R2. Is R2. Then R2 into R1 R2 is R1. Then you have R1 here. Is that correct? Yes. Equal to your 1 all over R. Then we can now proceed by finding the LCM of R1, R2, and R3. R1, R2, R3. So R1 plus R2 plus R1 into R1, R2, R3 is R, R3 is R1 into, no, sorry, R2 into R1. No, let's take it one after the other to avoid confusion. I think at this point I can split this into 1 all over R equal to R2 all over R1, R2 plus R1 all over R1, R2 plus 1 all over R3. I think it's better this way, all right? It's better this way. So it's better this way, and the LCM here will be R1, R2, R3, and R1, R2 into R1, R2, R3 is R3 plus R1, R2 times this will be R2. Then R1, R2 into R1, R2, and R3 is R3. And you have R1, R3. So we can move on. Let's quickly delete this. And then we can have more space to solve. And now you have your new look equation is 1 all over R equal to R2, R3 plus R1, R3. Then you have plus R3 into R1, R2, R3 is R1, R2 times 1 will be this. And you have plus R1, you have plus R1, R2 all by R1, R2, R3. Is that correct now? So we can, in the same vein now, find the, is there anything common? R2, R3, R3, R2. So we can find R3 is common here. R3 is common here, so we can say 1 all over R, 1 all over R is equal to R3 is common, open bracket, R1 plus R2 plus R1, R2. Let's quickly erase all this. Let's quickly erase all this. So we have all by R1, R2, R3. And we can now solve our effective R. By cross multiplying, you have R1, R2, R3, all by R3 open brackets, R1 plus R2 plus R1, R2, right? Equal to your R. So I have this beautiful expression for the effective resistance for a set of resistors that are connected in parallel. So this beautiful expression can be used to solve. Let's do this. You have your R equal to R1, R2, R3 divided by R3, open bracket, R1 plus R2, close bracket, plus R1, R2. And this can be used to solve a problem of this magnitude. So we can equally use this now to solve. We can solve 5 times 6 times 3, open brackets. Let's try and use it to solve this particular problem and see if we can still arrive at the same answer we got earlier. So let's delete here. Let's erase and see how we can slot that in. And I think we can still arrive at the same answer we got earlier. So our R is equal to R1 is 5 times our R2 is 6 times our R3 is 2 divided by our R3 is 2. Open bracket, our R1 is 5 plus 6 all together. R1 is 5 times R2 is 6. So 5 times 6 is 30. 30 times 2 is 60. 30 times 3 is 60. It's 60, so we have 60. We have 60 divided by 22, divided by 22 plus 30. 5 plus 6 is 11. 11 times 2 is 22. Is that correct now? So we can now solve 22 plus 30. 22 plus 30. You have 52. You have 52, so we can solve 52. So we have 60 by 52. And what can go? You have 2 here, 30. 2 here, 2, 6. 2 here, 15. And 2 here, 13. So you have your R to be what? 15 over 13 ohms, which is correct. Very correct. Very, very correct. So you can see now that this relation can be used to solve for the effective resistance of set of resistors, three that are connected in parallel. Thank you very much. Let's move on. Let's move on. I can take care of this now. Let's move on. We've validated that point. That point is valid. It shows what we solved earlier, and using this formula, we're arriving at the same answer. We're arriving at the same answer. Arriving at the same answer. So let's quickly move on to the next problem. Let's quickly move on to the next problem. Because of time constraint, we might not be able to solve the fourth problem, which is the 15 ohms resistor that is connected in parallel with a 2 ohm and a 4 ohm resistor. But I do promise you that in our next class, we are going to do more of these particular problems. We're going to do more of problems with respect to resistors, current, and potential difference. Do take good care of yourself. See you in our next class. God bless you. Thank you.